Hello everyone, in this tutorial video we are going to study about some of the types of the aquifers like confined aquifer, unconfined and perched aquifer, and some problems related to this. So let us start this tutorial video with some of the types of aquifers. As we have already discussed, there are basically two types of aquifer depending upon whether they are confined or not. So if our aquifer is unconfined, then it is known as unconfined aquifer, and if it is confined by certain layers of impervious layer of the saturated formation, then it is known as confined aquifer. As you can see here, this is the example of a confined aquifer where it is confined between two impervious layer. Next thing is that it is also known as artesian. So what is basically is the artesian? So artesian is basically defined as the upward movement of the water under hydrostatic pressure in the rock. So if the water is being confined in this pressure, in this area, then water is under pressure. So if you try to dig in a well in through this impervious layer, then the water will come out under certain hydrostatic pressure. So that is basically is the so we have got a term that is artesian, which actually signifies this principle. So in this case you see here that this is unconfined aquifer, which is non-artesian. Why? Because we don't have a confining layer, so that the water when digged out in this unconfined would come out from at an extreme hydrostatic pressure. Therefore it is defined as an non-artesian saturation formation. Next is the various types. As I have already discussed, that there are basically two types of the aquifers, basically unconfined and confined, or it is also known as non-artesian and artesian. Both are basically the same thing. Next is the first, unconfined aquifers or non-artesian aquifer. So as you can see here from this diagram that this is the ground level, and these are the wells that we have digged into the ground surface, and this is the water level. So here we have got two wells, well number 1 and well number 2, and this is the water table. So here the water table is actually equals to the water level in these wells. So in this case you can see here, this is the water level in the well 1 and this is the water level in well 2, which is actually is the same as the level of the water table. So this is an example of an unconfined aquifer where there is no any impervious strata. And so this is an example of a non-artesian aquifer. Also this is also known as gravity. These wells which have been digged through this unconfined aquifer is also known as gravity wells. So which are the water wells in these wells which equal to the level of the water table. So you can see here, this is the level of the water table and this is the level of the water in the well, and both are equal to each other. Therefore such type of the wells when digged in certain type of the unconfined aquifer is also known as gravity wells. Next is the confined aquifers, or it is known as artesian wells. So in this case, as you can see from this diagram that we have we have a confined layer of an aquifer which having confined between these two impervious strata. Those such type of the confined aquifer between the two impervious strata is known as confined aquifer or artesian aquifer. So that if you try to dig in a well through this impervious strata in this confined aquifer, then obviously the water has been enclosed in such type of aquifer under hydrostatic pressure, and when a well is dug in, then water will obviously come out under the hydrostatic pressure. So such type of saturation formation is known as confined aquifer or artesian aquifer. There is next other one thing that flowing well. So in both of these, we have a scenario here that we have a 3 wells that we have dug in, well 1, well 2 and well 3. In the case of the first well, you can see here that the water table and this dotted line is actually is the water table line. So in this case the water table crosses below of this water level. In this case the ground level is here and the water level is here, but in this case as you can see here, this is the water level and the water level lies above of the well which has been digged. So in this case the water will come out under the pressure. So such type of the well is known as flowing well when the water comes out under the pressure. Why? Because the water table lies above of the well. So this is actually the imaginary surface of the piezometric surface. So this is an example of the flowing well. Now next is the Perched aquifer. So this is the other type of the aquifer that is known as Perched aquifer. This is very uncommon type of aquifer that is found below the surface of the earth. As you can see here, this is an example of an Perched aquifer. Before of that you have seen confined and unconfined, but this is Perched aquifer. What actually happens in this Perched aquifer, that this is the ground level, and below the ground level we have a certain small section of the impervious layer which consists of the saturation formation, so that it holds certain amount of the water. And you when try to dig in the well in this impervious layer, then you can extract the water that has been stored over here. So this is an example of a Perched aquifer. So as you can see here that there is a limitation, there is a limited amount of volume of water which can be stored here over here. So that is a Perched aquifer. This doesn't have a tremendous storage of the water as like aquifer. So this has got certain limitation in the quantity of water that it can actually store. Next is the specific capacity and coefficient of storage. So what is specific capacity? How we can define the specific capacity? This is actually defined as the well yield per unit of the drawdown. We actually define specific capacity as the well yield. Yield means what is the amount of water that we can extract, volume of the water that we extract from the well, that is yield. So the yield from the well per unit of the drawdown, that is defined as the specific capacity. The next important thing is what is basically drawdown. So let us understand this drawdown by one figure so that you can better understand what is a drawdown. Let us suppose that we have got a aquifer over here and we have digged in a well, and this is the water table. So when we try to dig in a well in an aquifer which is having water level at this level, so what actually happens, the water level goes down. As you can see here, the water level goes down, and now the water level in this well is at here, not the water level will be at here. So this vertical distance that has been lost is known as drawdown curve, and that is indicated by this dotted line. So this is basically drawdown. So what is specific capacity? The amount of water that you yield per unit of the drawdown. So if you are trying to continuously extract water from this well, then this drawdown curve will go like this, again like this, again like this. So for the per unit of the drawdown, what is the well yield? That is defined as the specific capacity. Okay, now next terminology is the storage coefficient. So now what is storage coefficient or the coefficient of storage? This is basically defined as the volume of water that is released from the storage in a confined aquifer per unit surface area per unit decrease in the hydraulic head. So that is defined as the storage coefficient of storage. Okay, so now basically we have got certain two ways by which we can measure the yield of an underground source, that is aquifer. We have got basically two ways on the basis of the flow velocity of the groundwater that we had defined equation for that in the previous slide, and other is by performing certain kind of pumping test in the field, and by the help of both of these we can actually determine the yield of an underground source, let's say for example aquifer. So let us now do the first thing, that estimation of the yield using the ground velocity of the groundwater. So as in the previous slide we have determined an equation that is V equals to n times of Va, where n is the porosity and Va is the actual velocity of the groundwater. So we have calculated the discharge velocity. If we multiply that by the area, then we can actually get the discharge of the well, that is denoted by Q. So hence Q is N times VA times A. Now next thing is that so that is the equation that we have drawn via the Slitzer or the Hazen empirical equation. If you look in the previous video, then you can find out the equation of the Slitzer and Hazen, and from there we have derived this equation. So now let us suppose that we have got two observation well. One observation is this and other observation well is here. Okay, and there is a chemical pressure, means we have the water is flowing from this well to other, and we have dipped in a chemical so that when the water flows from one well to another, we can actually visually see if certain coloring pigment has been added to the water. Let the distance is s and the time is traveled by the water is t. So s over t will give you va, that is actual flow of velocity of the groundwater, and if k is the coefficient of permeability, then we can find out v equals to ki. Hence we can say that the permeability coefficient of permeability is v over I, where v is n times of va. Okay, now what is I is HL over the horizontal distance, where HL is the difference of the water surface of elevation of the two wells. So if we use this equation, then we can determine the or estimate the yield in certain type of saturation formation. Let us understand this via one numerical. So let us suppose that if in a field test the time taken is 6 hours by the tracer or a chemical to move from one aquifer to the one well to the another well in an aquifer, and if the observation well are 42 meter apart and the difference in the water level is 0.42 meter, now we have to compute the discharge velocity, coefficient of permeability, porosity. If the given porosity is 20%, then the coefficient of intrinsic permeability, and so on. So let us at first calculate the velocity of the groundwater flow, that is Va, that is equal to S over T. Then we can calculate the discharge velocity, that is N times of Va. Then we can calculate the hydraulic gradient, that is HL over S. Everything is given in the question. You need to just put the value. Okay, now from here we can calculate the coefficient of permeability, that is K. Since V and I are known, hence we can calculate the coefficient of permeability in centimeter per second. Now we have to calculate the coefficient of intrinsic permeability, that is K naught, which is equal to K times V over G. We know the value of all these things, just put the value and then calculate the coefficient of intrinsic permeability, and you can calculate its value as 3.96 into 10 to the power minus 5 centimeter square. So this was the one method in order to estimate the yield from the given saturation formation. There is another two methods to estimate the yield, which are by the pumping test. So we used to perform two types of tests. One is the pumping test and another the recuperation test, by the help of which we can actually estimate the yield. So in the first type of test, that is the pumping test, what we actually try to do, we have a well, okay, that is constructed through an aquifer. We have given a set of the aquifer and we actually have constructed a well through it. Okay, now there will be certain yield that we will try to just dig out from that well, and that will depend upon what is the rate of our pumping. So the rate of pumping is changed, whatever the rate of pumping by which we are yielding or taking out the water from the well is changed, and they are so adjusted that whatever the water level that is in the well is always constant, means we are taking out the water but the water level in that well is constant. So we will try to achieve that thing, and that is said to be condition of equilibrium. Now the rate of the pumping that one equals to the rate of yield, then we actually know that what is the actually the yield, because we know what is the rate by which we are taking out the water, and we also know that now the water level in the well is constant. So from here we can get an estimation that this is the yield. If we try to extract the water at this rate, the water level in that well will be same, but it is very difficult and almost impractical to adjust the such type of rate. So that is the first method, that is the pumping test. And the other method, that is recuperation test. This is the method in which what we do, the water is first of all drained from the well. Whatever the water that is present in the well, we at first drain that water at a very fast rate, so that there is large amount of the drawdown. Now what we do, we stop pumping and we let the water rise in the well slowly and slowly. Now that rise in the water in the well could be noted down against the time, and we can actually calculate, or just by looking the stopwatch we can see how much time had been taken by the well to initially what was the level in the well, how much time that water has again taken to reach that initial level again. So we know the time. So if we know the time, then we actually can determine what is the rate by which the water has been filled in that well again. So if we know the area of the well and the rise of the water table, then we can determine the volume of water yielded in that given time interval, and then in that given drawdown. So by working out on this method, we can determine the yield by a such type of method. So it is found that the yield is higher at the higher drawdown. So these tests are generally conducted during the driest period of the year. So if there is driest period in the year, then there will be higher drawdown, and in that case the yield will be obviously higher. So that's for today, and in the next tutorial video we will cover the different topic regarding the Thamium equilibrium formula, which we will apply in the confirmed aquifer. Thank you for watching this video.